We're going to go ahead and skip actually lesson 11.5. Right now we're going to kind of be doing some picking and choosing between now and the end of the school year. We are going to be learning about some of the trig functions, sine, cosine, and tangent before the end of school as well. So kind of right now I'm picking some things that you will use or possibly see in the future. And so here we go with section 11.6. This is on proportions with volume. And so similar solids are solids that have the same shape, but not necessarily the same size. That is what similar solids are. And so some characteristics here that I need you to get down. First of all spheres are similar. That's just a fact. All spheres are similar. So remember what similar means? What does it mean to be similar?
Same angles.
Yep.
It's proportional.
Yeah, everything, basically it's the same exact shape, but it's not necessarily the same size. Okay, that's what it says up here by definition. Okay, so spheres are always similar. Cylinders are not always similar. Okay, so the question is, why? Why are cylinders not always similar? You can have different diameters, right? As well as different what? Heights. Okay, so an example of cylinders that wouldn't be similar. You'd have a tuna can, right? You know those tuna cans, they're short and stubby? Compare that to a pop can. Are those going to be similar? No. No way. Because in a tuna can, the radius is much bigger than the height. In a pop can, the radius is much smaller than the height. So see, those are the differences. That's why cylinders are not always similar. Okay? Two polyhedrons are similar if all their corresponding faces are similar and the lengths of their corresponding edges are proportional. So let's talk about what that means. Their corresponding faces are similar. That means that if it's a rectangle on the face, then the other one has to be a rectangle. It can't be a rectangle and a square. Okay? It can't be a rectangle and a triangle. Okay? And the lengths of their corresponding edges are proportional. That's the biggest thing you need to get down today. Okay? All the edges are in proportion. And if they are not in proportion, then they are not similar. Questions? We're going to look at a few examples today, and then you should have some time to work on your assignment. So here you go. It says, are these right rectangular prisms similar? Yes or no? So what do you think in looking at it?
No.
Why no?
Because their proportions are off.
Because what'd you say? Okay, so first of all, let's compare the 7 and the 14. I know that in order to get to 14, I take it times 2, right? Okay, so let's look at this side. 3 and 6 correlate, and 3 times 2 is 6. Ah, great. And then I get to the 2. Ah, what do you notice about their heights? They're the same. They're not in proportion. So as a result, these right rectangular prisms are not similar. They are not similar because the height is not in proportion. So that's all you're going to be doing. Let's look at another example. Are these right circular cones similar?
Yeah.
So let's compare. This is the easy way. Let's start with our radii. So I'm going to go ahead and take 8 over 12. And I know in order for them to be similar that the heights have to be in the same proportion. So I've got 14 over 21, which is the height from this figure. So in order to see if they're in proportion, we're going to cross multiply and we're going to compare those numbers. So to cross multiply, I'm going to take 8 times 21. 8 times 21 is 168. I'm going to compare that to the other diagonal. What is 12 times 14? 168. Are they the same? Yes. So are these triangles similar? Yes, they are. Now, would you have to necessarily multiply along the diagonals? What's another way you could do it?
Is there like 3 halves of each proportional method?
Yeah, what you could do is you could just reduce the fractions down if you wanted. You could say you know that 8/12 reduces down by 4, so you end up getting 2/3, and that 14/21 reduces down by 7, so you end up getting 2/3. Sometimes that reducing down by fractions won't work if you're dealing with decimals. Okay, so understand that that might work initially, but you might have to go to this step later on. Okay, that's why we looked at it. Questions? Okay, we got one thing we need to add to our conjecture list. Okay, and this should make sense because of what we just got done talking about the proportions. If corresponding edge lengths, radii, or heights of two similar solids compare in the ratio. So now notice what it says, corresponding edge lengths, radii, or heights. If they compare in the ratio m/n, what do you think the volumes are going to compare in the ratio? So as you get those down, I want you to think a little bit. As you're thinking there, I want you to think of what the volume of box number 1 and box number 2 would be. So I know some of you are still writing. So as you're still writing, those of you that are done, I need you to look at those boxes. What's the volume of box 1? What is it? 1, right? Because it's 1 times 1 times 1. So it'd be 1 cubed, or 1 unit cubed. What's the volume of box 2? 27. So let's think about real quick, what would their sizes be? Or their sides be? What's all the sides in the first cube? 1. What are all the sides in the second cube? 3. So now what they're wanting you to do in this conjecture is compare those two results. And so instead of it being 1 to 3 and 1 to 27, they want you to say if the top is m to n, what is the bottom going to be right here?
N is n cubed.
M cubed to n cubed. Very good. That's exactly right. Okay, so they are in the ratio m cubed to n cubed. Or if you notice, we can write that as m divided by n, that quantity, to the third power. Those two are equivalent expressions. Bless you. So remember that. Okay, if the sides are in a specific proportion, the volumes will be in that same specific proportion. So let's go ahead and look at an example here and see what we got. It says the ratio of the weights of two spherical balls is 27 to 81. What is the ratio of their diameters? So if you remember on the other page, I started with the sides and I went to their volumes. Here I'm starting with their volumes. And I'm going back to their sides. So let's think about that. So here I am, 27 to 81. I'm going backwards now, so instead of cubing, what am I going to do? Instead of cubing, I'm going to take the, not the square root, the cube root. So basically I'm going backwards. So here's my m cubed, n cubed. I need to go back to m to n. So the easy way to do this What times itself 3 times gives me 27? 3. Okay. What times itself 3 times gives me 81? 4.33. Okay. So 4.3 repeating. Now, for those of you on your calculator that are wondering how you do this, okay, it's 27 to the 1/3, and then it will be 81 to the 1/3. Alrighty, questions? Okay, let's go ahead and look at this one. The ratio of the volumes of 2 similar prisms is 64 to 216. What is the ratio of their heights? All right, so we have 64 to 216. That's their volumes. So remember, that's m cubed to n cubed. What's the ratio of their heights going to be? 4 to 6. Good. And there you go. Remember how we found that again is we took 64 to the 1/3, or we thought of what number when multiplied 3 times gives me 64. Same thing with 216. What number times itself 3 times gives me 216? For those of you that are struggling, easy way to do this is start with 1. Just go through and start multiplying those out. Okay, some of you probably already have some of these memorized, and that could be the case. And then if you get to the point where you're not getting a number, you might want to use your calculator. It might be a decimal form. Alrighty, so this is what I need you to do for me for tomorrow. Pages 610 through 611, I need you to do 1 through 7. Okay, 610 through 611, 1 through 7. We're looking at a test sometime early next week, maybe the end of this week. All right?